Recording? Yeah, I think. I have a question. If in the beginning I will ask people to introduce themselves, should we start? Single press?
Information being because data is being collected.
So I would like to start before the title, introduction, introducing myself and the content of the tutorial, to make a proposal and to ask you a favor. So the second part of the tutorial will be with hands-on. So I will give you access to a platform, a digital twin, in which we try to implement actually the theoretical part I present in the beginning. And I would be very, very glad if you could contribute, participate as a game, let's say. So I show what could be the game. The game is up to you, what you are doing. So you have full freedom. So this is a didactical example. We arrive also in the presentation. So in here, it's about using satellite observation, of any kind of satellite observation, for one problem in one health. So generating risk maps for population of mosquitoes, which are coming now to Europe, which a few years ago they were not here. And these new species of mosquitoes, they carry pathogens. And in this moment, there is a preoccupation how to map, how to make a cartography of the risk of these pathogens. And here I put this didactical slide. So what could be an habitat of mosquito? So habitat of mosquito could be something where there is a lot of vegetation, there is water, there is stagnated water, there is humidity, there are conditions like meteo condition, like precipitation, wind, temperature. And based on this kind of mini scenario, using the tool I will open to you to generate your own scenario, your own toy, let's say, project, and to develop it. And if you could present this in 2-3 slides and send it to me. And also when you operate the tool, to provide any feedback for enhancing the operation. So that will be by the end of the presentation. Good. I go now back and I start. So today tutorial is about artificial intelligence, mainly physics-aware artificial intelligence. I make a short presentation now, but later I will go in detail. In my opinion, physics-aware artificial intelligence is a very particular field for Earth observation, but also for other instrument data. So because in medical science, in medicine, we have instruments like tomograph, echographs, and they have a physical principle behind. We have astrophysics, we have planetary observation, we have industrial instruments, which are providing images. And all this category of images, they are different from photography. Photography is adapted to visual perception, and we have many, many models for visual perception in computer vision in photography. But in here, we pass the border. These images, satellite images, are images which are carrying physical parameters. So they are actually a map, a two-dimensional representation of some physical parameters, like a sensor which is measuring the temperature of the ocean or wind speed. So these are the main differences. Now, I would like, from the very beginning, to acknowledge my colleagues, my teams, my team at Polytechnica University in Bucharest, the team of Geospace Tech. It's a research center for spatial information. We are working mainly responding to European Space Agency tenders, ITTs. Our field is going from radar, so we will build radars. We have a radar operated now in Grenoble on the glacier, bistatic with the Sentinel-1. It's a prototype for signals for harmony. It's one example. We have other ground-based radars and multistatic tomographic. We are doing signal processing for the synthetic aperture radar, artificial intelligence for Earth observation, and we also have projects on quantum machine learning. I also would like to acknowledge my colleagues and my team at DLR, the German Aerospace Center. Part of the work I present today was initiated with my team on data intelligence and knowledge discovery in Oberpfaffenhofen. Part of this work was in cooperation with Munich Aerospace, which was a joint lab of DLR with the Technical University of München, TU München. And also I would like to acknowledge the French Chair of Excellence, Blaise Pascal, where I was working in Paris with CNAM, Conservatoire National Art et Métiers. That is a visual summary of the tutorial. So I will start with the concept of explainable and physics-aware artificial intelligence for Earth observation. I will present some elements of super resolution. I will go over the digital twin concept. And at the end, if there is interest, I will present 2 or 3 slides on quantum machine learning. I summarize here, and I will provide also to you several recent publications. These are articles in IEEE Geoscience Remote Sensing magazine, articles which are presenting not the research result, but they are presenting a new concept, a perspective, new paradigms, an overview, and a conclusion what to do in the future. So, for instance, the artificial intelligence to advance Earth observation, it is an article together with colleagues from TU München, DLR, EPFL, the Swiss Federal Institute of Technology in Lausanne and in Zurich, on behalf of being a visiting professor with a PhilLab at ESA. And this paper presents a vision of ESA for artificial intelligence in Earth observation. And the others, they present also vision, so starting on existing technologies and methodologies today, theories, what is going to happen, what we expect to happen, which has a direction to be developed from mission in space, because missions are influenced now by artificial intelligence. So it will be onboard processing, communication between satellites, physics-aware paradigms on how to embed the knowledge about the orbit and the instrument knowledge, instrument design in the algorithms, on generative models, and also on new methods in machine learning like active learning. So I start with a very short movie to present actually the problematic of big data and artificial intelligence in Earth observation. I will let the movie with original sound, and at the end I will explain, or if you have a question, we can discuss about. But in the beginning, I present this movie as an introduction of the problematic of big data in satellite Earth observation.
Information being lost because data is being collected that can never be analyzed. The German Satellite Data Archive near Munich contains vast amounts of valuable data collected over the past 30 years. The archive can store more than 50 petabytes of data on magnetic cassette tapes. It may be that these tapes hold the answers to questions that won't be posed until sometime in the future. But when that day comes, will we be able to access the data? The more data we save for later, the greater the risk of losing information forever. Even the best storage media can age and become obsolete. But maybe there's a way to master the deluge of archived images and virtual reality. Researchers are mining the Satellite Data Archive, hoping to make its information more readily accessible. As if the archive were a library with open books lying before them, the scientists can pick out an image, dive into it as it were, and check to see whether it shows structures similar to those on other images. The computer works like an automatic sorting facility. It searches the images for components like vegetation, farmland, bridges, and water. The computer sorts the images into stacks and categorizes them by their content.
At the present, they probably store in archives more than 10 to 20 millions of satellite images acquired after the 80s. With a new era of the Sentinel satellites of the European Space Agency, the data volume per day will reach the level of 10 terabytes. This is our data rate. So we are going to reach soon thousands of petabytes of data, which is a large volume of data, and all the research community is putting huge efforts in dealing with information extraction.
Soon, we will no longer be talking about millions or billions of images, but trillions. And then it will be more important than ever to uncover meaningful information hidden in the mountains of data.
Okay, so this is a problematic of Earth observation. So we have a continuous growing big data, and the technology is following. And we expected, at the beginning of this conference, for instance, in 2014, I think, we expected to have an increased percentage of used interpreted satellite images. But because the satellite images technology is developing, we have a competitive course. And we still stay at some 10% maximum of using. So volume is growing fantastically. Technology is trying to follow this expansion, this explosion of data and complexity. However, a limited number of data sets arrives to be really going in application. And it's now the big data together with artificial intelligence trying to bridge this gap. Now, in this short movie was broadcasted on ARD, the German television, and on Arte, the German-French television. The movie was a result of a project involving 4 PhD students for a period of 4 years. The project was immersive visual data mining. So what you have seen, it is not a classification. So we represented images in a multidimensional space, thousands of dimensions, because images are very complex. And the problem was to project from 1,000 dimensions in 3 dimensions, in the cave, in such a way that in front of the PhD student to bring together all images were similar. So when the PhD student looked to an image with a coastline, ships or football terrains, the system understood, was learning how to project 1,000 dimensions in 3 dimensions in such a way that similar images are coming in front. It's not a classification. It is learning how to project from many dimensions in 3 dimensions, and later to navigate. So it was a demonstration of new machine learning and technologies to explore rapidly very large volumes of data. It's like diving inside the disk of our computers. Again, please, if there are questions all the time, ask a question. Here I went back to the paper of Claude Shannon, a mathematical theory of communication in 1948. So in 1948, Shannon noticed that messages, they have meaning. And this meaning has conceptual and physical content. But at the time, Shannon told that these aspects, semantic aspect, meaning and physical aspects, they are not relevant for communication. Today, everything which is happening in communication, it's about semantics. Semantics with the aspect like semantics, meaning, but also semantic like in our sensor, semantic physical quantities. Because from our sensor data, we extract cyanobacteria concentration, humidity. And all these aspects of semantics, they are now one of the key part of the technology we develop, because actually what you have seen in the movie, it was a communication channel. We have 1 zettabyte of data, and we have to generate a code in such that this zettabyte of data is compressed presenting to us, the users, in such a way that we can understand this big volume of data. So it's a coding of the data to extract some meaningful information. I go now and I exemplify the physical nature. So the left images, it's a picture of a landscape, a mountain, and on the bottom is a synthetic aperture radar. It's a composite, color composite image. And the question it is, how much knowledge we need without looking, without knowing the landscape only from this image to be able to draw the landscape. So someone is showing to me a synthetic aperture radar of the landscape, gives me a paper and a pencil, and asks me, draw what you have seen in the data. And it's an example of the complexity of our sensors. So our sensors, like synthetic aperture radar, but optical, they are not sensing, they are not generating a picture, an image of the object. They are representing in 2 dimensions the scattering of the object. It's a doppelganger. Because what you register, it is a reflection. And in synthetic aperture radar, that is like in the right, it's a Terrasar X image of the Parliament House in Bucharest in 1 meter resolution. These are signatures, which are represented in Fourier domain. So we have like an echo, and that is for all satellite sensors. So they are not a projection, an image of the object, they are a record of the scattering of the object. So we need to understand how the scattering works. Based on this observation, another example, this time from optical on the left side, is Sentinel-2 data. Sentinel-2 data, they have 13 spectral bands. Visual perception, it's limited to 3 bands, RGB. And in the upper image, in the left, there are circles marking 3 areas which visually are different. On the bottom, there are 3 areas which visually they are identical, similar. If we apply a method of information theory to compress this data, we obtain 2 images in false colors, which are compressing all the information from 13 bands in 3 bands. And what we see that actually the areas which looks to be different, they are similar. Why? They are different in 3 bands. And 8 bands, the remaining 10 bands, they are similar. And images which are similar in 3 bands, visually, they are different in reality because information in the rest of 10 bands is different. So it's an example on how we differentiate the notion of picture from the notion of satellite image because there is a physical process. In this field, in this area, the example on the right is an example of using a gun. Guns are used, they are coming from computer vision, and we can reproduce images. We can copy and generate a synthetic image. However, this example is an example on Terrasar X, a German mission, in which we tried to train the gun not to reproduce the object, but to reproduce a signature, like double bouncing or multiple reflection, corner reflectors, side lobes, because we need to learn the signature, not the object itself. So these examples, they conduct us to the concept of sensory and the concept of semantic gap. So the sensory gap is the difference in between the sensor, like hyperspectral data, multispectral radar, scatterometer, and the visual understanding of the image presented like a map of pixels extracted from this signal. So we have a sensor and visual perception. And we have to bridge this gap. So our visual perception is not adapted to synthetic aperture radar. Synthetic aperture radar is about Doppler frequency. We need to hear, not to look at synthetic aperture radar. And the semantic gap, it is the assumption we have when we design an algorithm that the algorithm will capture the semantic of the scene we observe. Semantic means also meaningful in sense of physical parameters. And again, in here, expectations are not always true. Why? Because the image itself, it is not the image of the object. The image, it's an image of the scattered field. And that generates a difference in between the semantic. On the bottom, it's an example of a classification which is combining classes like woody, mixed artificial specular surfaces. It's combining with a type of scattering in a polarimetric. And it's an example obtained with a network latent Dirichlet allocation, in which we have the class, but also we have the percentage of scattering. So it's 53 multiple scattering, 34% of volume scattering. It's an explanation, quantitative, in terms of the physical signature, because what we see in the image, it is a signature. And in here, we give also a quantity for, and that is now further developed in the part of artificial intelligence. Machine learning. Machine learning needs training. For training, we need to have training data sets, and for the validation of the algorithm, we need benchmarks. In computer vision, we have now databases with tens of millions of pictures who have been annotated. This annotation is done by crowdsourcing. There are 1 million of people, they annotate objects in pictures. In remote sensing, it's very difficult for several reasons. Because picture, finally, it's the same, does not matter if it's a picture taken with a professional camera, photographic camera, or with a smartphone. The pictures, the properties are the same. There are definitely differences, but not in the respect to this training data set and benchmark. In remote sensing, we deal with sensors with a different number of spectral bands, different spectral bands, different resolution, from microwave to infrared gravitational sensors. And actually, the labeling is not done visually. We don't have 1 million of experts to make a crowdsourcing. And even we have 1 million of experts, we need to make the labeling with physical parameter. We need to estimate chlorophyll. We need to estimate moisture. And these are quantitative physical parameter. And that's why, in my opinion at least, the benchmark and training data set, in Earth observation, it is a standalone field. How to generate such a benchmark. So we are very different from computer vision. And that is an example of a taxonomy on how to go from image to the physical parameter. That is a reminder of the multiple application of satellite images. There are thousands, tens of thousands. Difficult to evaluate where satellite images are used. They are used in almost every digital system we have, and they are covering from medicine to agriculture, to ocean observation, to climate. I mentioned only the big aspects, biosphere, geo and lithosphere, hydro and cryosphere. Why? Because these are impacting all the human activities at a global scale. And examples are ecosystem, monitoring from space, natural reservation around Europe, deforestation in Brazil, important for the carbon, subsidence, the measurements of millimeter precision with synthetic aperture radar of vertical displacement, horizontal displacement, due to the exploitation of resources or natural, and definitely monitoring the sea ice, which are the factors in climate. So I mentioned only these. Applications are many, many. I want to stop one moment to satellite image time series. So now we have more than 50 years of remote sensing, satellite remote sensing. So almost every place of the Earth was observed over the time. So we have movies from space. After Landsat and Sentinels, we have very dense acquisition. Every 2 weeks, for synthetic aperture radar, every 10 days, or now with 3 satellites every 3 days. For optical, depending on the cloud atmospheric condition, we have also very long time series and dense time series. So today, the product of Earth observation, it is not anymore an image, a product of Earth observation, it is a time series. And I try to run the movie. So that is Bucharest observed from 1984 to 2012. Landsat time series. It's a history of 30 years. So it's a volume of data. It's a hypercube because we have space dimension, we have time dimension, and we have spectral dimension, and we have dimension of meaning inside. And we need specialized tools to analyze this. So that is a product. So it's a standalone product. So image is not a product anymore. Every place is observed with this kind of movies. And we have a huge quantity of information. And this information is quantitative. These are spatiotemporal patterns which could be extracted from this. And there is a trend in computer science, in signal processing, to develop new methods. Many of them artificial intelligence. If we look now, the progress in foundation models go to very complex algorithms, very large models. However, we need also to look in the basic theoretical aspects which exist. Even some of them, they are very classical, and try to identify which are very simple methods. And in here, I present only this. It's a compression-based pattern recognition. The database with airplane images, it is classified using only one operation, data compression. So we take each of the image, we compress it with gzip, and we write down one number, the length of the compressed file. Later, we take one image and put it together, concatenate with all the other images, and for the pair of images concatenated, we compress and write down another number, the length of the compressed file. And this k of xy, it is the length of the compressed joint files. K of x and y, they are the length of individual compressed file. We compute this d, which is a distance. And this distance is independent of the data. This distance can be applied for any digital string. We need only digital strings. It does not matter if it's polarimetric picture or text. It's a digital string. And we have a classification which is independent on the features. We have no feature extraction. It's using all the information as a data. And also we don't have a classifier, because always when we are doing a classification, we ask which classifier we used, which feature have been used as the input of the classifier. And this is a very simple method, information theory, and we need not to forget this field and to find solutions which are adapted, complementary to artificial intelligence. That is an example on big data. So in Earth observation, we have many architecture, like deep architectures, which are combined with active learning. We extract features, and in active learning, we are giving positive, negative example. We combine, let's say, deep learning with, let's say, classical methods in machine learning and the classification. So that's it is a message of ESA. So ESA stated that today we are in the era of digital twin Earth, and we need to look and develop technology in quantum computing and artificial intelligence. So in history, we have been, let's say, in the 90s, in the period of neural networks. After the period of neural networks followed the period of data fusion. After the period of data fusion, there was data mining. After that started the period of big data. After the big data, we have artificial intelligence. And now we put everything together, all this knowledge, in large systems, which are digital twins, which are combining simulation, numerical models, what-if scenarios, with a prediction, with time series analysis. So we have now in the last, let's say, 7 years, we have the technology and the knowledge how to go really in analyzing big data in the true complexity. A very short reminder of satellite sensors, a taxonomy. So we have on the right side very high resolution images, which are closer to computer vision, because in very high resolution images, the objective, it is to recognize patterns, objects. So this is a field which is bridging computer vision and Earth observation. But Earth observation is characterized by sensors which are very specific, which are measuring sometimes only one physical parameter, like ozone concentration, ocean temperature. So I have sensors which are dedicated for one physical parameter, or for geometrical parameters like interferometry, tomography, and stereo. We measure the height of the terrain, again one parameter, but precisely measured over the globe, displacement, subsidence. And we have sensors which are in between. We have sensors which have high resolution. We extract patterns, we recognize structures, objects, but also we extract physical parameters. We have a combination of both aspects, physical, geometrical, and pattern like computer vision. I don't know if there are questions or comments. A reminder of the problematic in understanding and developing algorithms for satellite data, the sensory and the semantic gap. And an example. So on the very left image, it is a TerraSAR-X synthetic aperture radar, 1 meter resolution. And we make a visual exercise. So in this image, I can see 2 patterns, which are 2 bright lines on the right and left. And like a computer vision and image processing algorithm, I could tell, look, in this image we have 2 similar structures, 2 times parallel bright lines. We have from the same area, it is a train station in Munich, we have a very high resolution optical image. So in the very high resolution optical image, we don't see similar patterns. We see a double bright line on the right and a single dark line on the left. We take OpenStreetMap, a thematic map. In the thematic map, we see the railway, but it's nothing indicated, but the right we have a bridge, because it's a traffic map, thematic. Not all information, it is in the thematic maps. They are dedicated for some objectives. Later, we have a picture from the blue point. It's a Lucas database in this direction. And in the picture, we notice that actually this left structure, it is a support for the power line of the railway. So now what we have. So we have 4 different categories of data, and we have the following problems. So many times we want to have multiple observation, and from multiple observation to have better understanding, better information. But we have also some challenges. So in the synthetic aperture radar, the images are not images of the object. So that are strongly affected by scattering. So these images are images of the signature of the object. So we need to have some knowledge in between the signature and the object. Information in between synthetic aperture radar and the optical data, it is contradictory. So if I would like to fuse the left image with the SAR, with a multispectral, and I'm giving training examples, this training example will be contradictory. Sometimes I want to classify the same. Sometimes they are contradictory. Sometimes they are double bright. In optical, it's single and dark. And the other right it is a highway, or the bridge. This corresponds because we have two bright lines, both in optical and SAR. So we have an example which is positive, the other is contradictory. We have incomplete information. Some of the thematic maps, they do not observe, they do not record all the details in the scene. And we have very different multimodal information. Optical and SAR maps are already multimodal, but if we have a picture on ground, we have a picture which is not from the top, it's on a horizontal, and it's completely different in modality. So what to do? So if we make a data fusion, we need to have a data fusion which understands contradiction, incomplete information, and multimodalities. And I will show examples of such algorithms. Or if we have a single sensor that is about the physics aware, we need a machine learning which is not learning in the left image, in the SAR image. We should not learn similarity in between the image objects, the two parallel bright lines. We need to learn actually how this was generated. When the right pattern, it is one single reflection on the train, on the railway power line. The other is a double bounce. And actually, the machine learning we develop should be a machine learning which is not understanding double line like computer vision, visual perception, should be a machine learning which is learning that is a single scattering or a double bounce. And this is a difference in between physics-aware machine learning, artificial intelligence for Earth observation, and computer vision. So in computer vision, we understand the object in the image. In Earth observation, in the image, we have scattering signatures of the objects, and we have to understand how this was generated. So we have a layer, a physical layer, which is making the connection in between what we see in the image, the structure in the image, and the object itself. That is a very short introduction on synthetic aperture radar. Is anybody working in synthetic aperture radar? Good. I make a very short introduction. So we take a radar system, like a radar, like the traffic radar, which is transmitting microwaves. Frequency, it's many times similar with the frequency on the mobile telephony, so let's say 9 gigahertz. It's transmitting a pulse. The pulse, it's propagating, reflects on ground, and it's returning to the antenna. What means synthetic aperture radar? Synthetic aperture radar, it is a field in computational imaging. So we do not obtain a picture like a pinhole camera. So we have an object, we put a pinhole or a lens, and we obtain the image of the object reversed and scaled depending on the geometry of the system. In synthetic aperture radar, we are computing the image. We have a signal, and this signal will be transformed. And I answer a simple question. So these 2 points on ground, they reflect the microwave, and the echoes are arriving at the antenna in the same moment because it's symmetric. So it means that here I sum up 2 signals. Now the question is, could I separate these signals? So this is a question of synthetic aperture. And the answer it is yes. And why? Because this platform it's moving, has a certain speed. And if I decompose the speed on this direction, I obtain a vector. And if I decompose the speed, I obtain another vector. And we know the Doppler effect. So if the microwaves are reflected on an object which is moving, the reflected wave is changing frequency. This means the echo from this point has another frequency compared with the echo of this point. And this means I can synthesize an image, I can separate them, I can resolve, I can see the 2 points by measuring the frequency. And that is a principle of synthetic aperture radar. It's very, very simple. It's like a Fourier transform. Now, what's happening? Because of this very simple principle, the synthetic aperture radars, they have very practical and physics-based property. So if I take the complex values in synthetic aperture radar, because the echoes, microwaves, they have amplitude and phase, and I take the Fourier spectrum of the synthetic aperture radar, and I cut the spectrum. So that is our Fourier spectrum. That is omega x, omega y. That is the direction of the flight. So if I take this Fourier spectrum, and later I take this part, and I compute the inverse discrete Fourier transform, I obtain 2 images. And these 2 images, they have the following property. They are equivalent with 2 physical antennas. One antenna which is looking in this direction, and the other is looking in the other direction. So this is a very simple physical property based on this principle of the Doppler. And what's happening if I'm transmitting and looking to an object from different angles? If I'm looking to an object from different angles, I obtain additional information for recognition, even in optics. If I'm looking from this object, from this and from this, I obtain like a stereo. I can reconstruct a 3D. I have another feature. I have an enhanced feature from this. And now, this very simple property, so it's just computing a Fourier transform and cutting the bandwidth, is equivalent with 2 antennas looking at different angles. It is embedded, it's a model I know, and this model, we are going to embed it in a, and actually the short movie shows a pattern, but it's not a moving pattern. It is a spectrum of the Fourier, which is changing while antenna is flying. So if we compute the spectrum Fourier, we observe changes on the scattering, on the signature of objects, depending on the look angle. So in here, I stop at a very first conclusion. In satellite observation, the image understanding requires the knowledge of end-to-end system. So we have to know the instrument. We have to know the frequency, polarization, number of spectral bands, hyperspectral, look angle. We have to know the principle, because there are different type of cameras on sensor, different type of recording. We have to know the orbit. We have to know how the data was processed, because our images are actually products which have been corrected. And we have to know how the correction was done. We have to know actually how the metadata, because in the metadata we have information about all. We have to know how to access the data in the platform, and we have to know the models of the physical parameter we want to extract. Because if we want to measure moisture or canopy height, we need a model behind. And actually, we have to put all this knowledge. So satellite image processing cannot be done in isolation. So I take an image and I process it, like in pictures. So we have to know all the end-to-end mission. And actually, that is now the concept on how to embed this knowledge in the models which are developed. Questions or comments? We have a break at 3:30, I understood, for a coffee break, and there is some coffee which is prepared. If you want to have a break in between, just tell, and you can make some 10 minutes, 5 minutes breaks. No? Okay, we go ahead. Now, that is the new paradigm proposed in this article for synthetic aperture radar, but it is very similar for any other Earth observation sensor. It is a paradigm in which we are modeling the physical layers of the Earth observation system. And in these physical layers, we embed the knowledge of the instrument and the orbit, the movement of the platform. And this becomes very, very important, even more important for formation flying and constellation of satellites. We have all the part of signaling propagation. For radar, the type of signal, propagation to the atmosphere. Propagation, it's a Fourier transform. For optical, or interaction with the atmosphere and consistency. And we have the interaction with the scene. So the property, the material properties, which are actually copied in the signal which is reflected to the antenna. And these are the models we have to embed now in the artificial intelligence algorithms. So based on these models, we developed a paradigm which is using the knowledge of existing models like closed form, like the example with a Fourier transform of a SAR image, and the models of very high complexity or with too many parameters because of the observed scenes, they have high complexity, like a urban area. These models we learn from the data. So we combine in a hybrid algorithm existing knowledge, physical or mathematical models, together with models which are learned by deep learning architecture. And we are using the deep learning targeted for the part of the model which cannot be formalized in a mathematical formulation. And in here we have this loop in which we are using, for instance, the knowledge of the property of the Fourier spectrum or the knowledge of the polarimetric scattering. And we are learning from the data the high complexity scattering. And in here we have an example with bridges. So a bridge in the pair of images on the upper, there is a single bridge, and in the SAR image we have 3 reflections. Another bridge on the bottom, in the optical image we have 2 patterns, and in the SAR image we have also 2 patterns. Why? Because this depends on the relative position of the bridge in the antenna pattern. And these models now, they are encapsulated in this, and we can separate, understand actually that this is not a structure with 3 objects, but it is a single object, a bridge, which has multiple reflections. These are examples of different structures. In the optical images, that is visually clear, they are different. In the synthetic aperture radar, these are Zhou 3 Chinese satellite 1 meter resolution. In the satellite, in the SAR images, the structures are very similar. However, if we compute a Fourier spectrum, the Fourier spectrum is very different. So the visual is not enough. We need to have the spectrum analysis. And with these concepts, we develop a method of training a network, which is unsupervised in the sense that it's supervised in a different way. Unsupervised in the sense that we do not need labeled data, but we apply at a training phase the Fourier spectrum, the spectrogram, and the polarimetric signature, because both of them, they are translating object in signature. And we train the network with these parameters, which are actually the physical layers in the model. And we apply in here, we train a network with a quad pole, with a full polarization, which is, let's say, not very easy to access operational sensors, and apply this to a single or dual pole. And we generate a virtual sensor. So from a single polarization like Sentinel-1 data, we generate a quad pole data, an unobserved data. And that was done because the algorithm was correlating the spectral pattern, the Fourier, with a polarimetric signature and with the context, the spatial context. Each object with a certain shape is likely to have a certain signature. And the algorithm is learning this diversity with many, many parameters from the data, and is correlating with these physical parameters, which are computing very simple by a covariance or a Fourier transform. And again, that is a virtual sensor, a sensor which observes signature which is not observed by the sensor itself. So this algorithm could be finer refined, and we include the moving window for the Fourier transform in such a way to have all aspects of the antenna look angle for the scene diversity in the look angle. Further, we add supervised learning. So we have on the bottom a layer learning from Fourier spectrogram. In the middle, a layer learning for complex data. Unsupervised learning from diversity of the data with no label. And on the top, we add another layer, another network, which is learning supervised semantic labels for the data. And what we obtain a new classification, a new classifier, a classifier for CIs experiment. Why? Because CIs is very difficult to label. I mean, in a urban area, we can label data, but for ocean and for polar remote areas, it's very difficult to obtain a trustworthy and large training data set. And here we have a small training data set, and we obtain the classes like all-diced CIs, iceberg, and so on. And for each of the class, we have an explanation. What kind of scattering was responsible, was a cause for this classification. And we have the double bounce, Bragg, and so on. So we have a physical layer which is explaining the training, the result of the data. So this was an example on how to embed the physical models and generate new kind of results from the data. So this virtual sensing and this explainable extracting semantical classes and also classes of physical scattering. This is a deep learning architecture for complex valued signals. Now, we notice that synthetic aperture radar, it is not only a signal which has amplitude and phase, a real and imaginary part, but it is a signal which has properties due to the image formation. This Doppler differentiation of the targets. And these are examples of complex valued deep learning, convolutional, and an autoencoder. Definitely, they are implemented according to the algebra of complex numbers and statistics of complex numbers. But the network is more than a network for complex value signals. The network has the following properties. It's learning the azimuth decomposition. So if we make the Fourier, compute the Fourier transform of the generated data in the network, and we split this in the two subbands of the spectrum, we preserve the property of the antenna. So the network was not learning complex numbers, but was learning the property, a target. It's seen different in different bands of the spectrum. The basic property of synthetic aperture radar is coherence, the preservation of the phase. And actually, the generated data in this architecture are preserving the phase. We can compute interprogram coherence. It's in between 0.9 to 1. So it's a very good preserving. So this is an example on synthetic aperture radar, how it's learning from the data a physical principle and is able to reproduce this physical principle. An example of physics-aware algorithm for optical data. So we have the previous example with ambiguity in between visual perception and classification and the full 13 bands for Sentinel-2 for processing, for analyzing. And in here is an example of atmospheric effects removal, like cloud, fog, or ashes, or smoke from vegetation fires. So in literature, probably already knows this, there are different methods how to remove clouds. And these are mainly two categories. One is time series. I observe the same area, and I make an interpolation, a prediction of the area which is covered by the cloud. Or I'm using generative models. I train a gun or another generative model, and I'm filling the area covered by cloud and the shadow with a new data. But neither of these two methods preserve the information in the data. They generate artificial data. I don't know what is under the cloud. So I generate a nice uniform coverage, but the information which was generated is not real. It's not actual data. So in here, this is a very simple method. Is a very simple network which is using all the spectral bands of the Sentinel. And we know that sometimes, depending on the size of the particles in a cloud, fog, or smoke, there is a diffraction. So the infrared could penetrate to the cloud. And in here, we use all this information, compressing in the 3 bands, and we obtain a false color image, which is removing the effect of the obturation. And this image is real. So if I have an object, I can detect this object. So it's not artificial interpolation over the data. So I can really reuse as much as possible information in the multispectral data. And this is obtained, if you want, it's a very simple principle. The network, it's using the spectral angular distance. So many times in classifiers, even in deep learning architecture, we use Euclidean errors. In here, the error was computing the angle between the vectors, which is a very classical method for spectral analysis, one of the very first, with starting with Landsat. And this is a physical property, because in here I separate actually the signature, not the intensity. So it's about the wavelength I detect. And that result in this algorithm. An example on a time series. So that is a city of Bucharest. If you watch the dimension of the city from 84 to 2012, you see that the urban area is growing about 5 times. All the infrastructure, road infrastructure, airport, highway, even you can see a political change. So agriculture before 89 was different from agriculture after 89, because there was a change in the property. And you can detect this from the satellite. From the satellite, you get fingerprints of indirect observations. And actually, what we extract from this data? From this data, we extract patterns. And a pattern is not anymore a pattern on ground, like the street network of a city or the shape of a lake. A pattern, it is like in the upper. A pattern, it is a transformation of a natural landscape, progressively in a working area, the second one, image with a bright, in an artificial lake. And after a few years, the artificial lake is surrounded by a residential area. And that is a pattern, transformation of a natural landscape, an artificial lake surrounded by a city, residential area. The same for the middle. It's a parliament house in Bucharest, a working area and transformation in architectural complex, and the transformation from agriculture to residential area. And all this information, which is extracted from satellite images, it is always interpreted together with other information. In this case, with demographic information, because this transformation has consequences in urban planning. So if I have a new residential area, I have to build all the transportation network. I need to build all the commercial infrastructure. And this depends on density of the people and how they move around the city. And these are examples on how remote sensing and artificial intelligence goes again beyond image. They go in applications. That is another time series. It's a time series of synthetic aperture radar on the Black Sea. And from this data, from this time series, we can observe the water surface. And the water surface, it is actually the reflection. It is affected by mainly two phenomena: wind, provoking waves, and sea currents. And these parameters are physical parameters, and we'll see immediately how these physical parameters are extracted. And from such a synthetic aperture radar, I can extract a map based on the Doppler of the surface of the sea moving direction, and on the waves and the maps of the wind. I go now and I present an example on data fusion and time series. In the beginning, the data fusion is affected by these, let's say, challenges. Data from different sensors, they could be contradictory. So I cannot learn from them. So one sensor is going in one direction, is learning the other. And the same type, the same object could have different appearance even in the same sensor. I give an example on water. So water in optical data could have any color. So water could be blue, green, brown, red, any color. I mean, if you look to rivers or lakes all around the world, you will find water bodies with any color. In synthetic aperture radar, water could have any backscatter because it depends on the wind. So if it's a calm day, it's black because it's a specular reflection. If it's a strong wind, I have a strong reflection, could be sometimes as strong as a urban area. So this means that if I go in the training data set with example of water coverage and I use them, the machine learning will not understand. Why? Because one example tells water is blue, the other tells water now is brown. And this is a contradiction. Later we have incomplete data. Some of the data we are using is incomplete. So contradictory, incomplete. And we have multiple modalities. So actually, the simple example is radar and optical. They are completely different in sensing in physical principles. And all these aspects, they are becoming an important challenge in data fusion. So these are three paradigms on how to make data fusion at different levels. We can fuse the data directly at the beginning, so combining the data as the input of the classifier. We can fuse the level of feature extraction. And here I give an example for water. If we extract the spectral index, the normalized water index, in this case, the water is not anymore appearing like different colors. I have an index for water. If I extract from synthetic aperture radar a feature which actually is related, is removing the influence of the wind, I have two features and I can remove this contradictory component of the data. No, I'm lucky, no call. Or we can have high level fusion as a semantic. So we make interpretation, we obtain the object, and we combine them after recognition. So we recognize the object and we make the fusion after the recognition of the object. Now, the new products in Earth observation are time series. And that's an example on agriculture, in which we are fusing and making prediction from time series of Sentinel-1 and Sentinel-2. We need to have a layer of latency in which we are combining the features which are different from optical, so the common components, which today is a basic component in the foundation models. And to this model, we have an attention layer, which is actually able to understand what is contradictory and what is not. And in here we have on the bottom part the highest attention images, which are the images in optical and SAR, which correspond for the training. They are not contradictory. And the attention level is actually removing from the training these contradictory examples, which are in here, which are the lower attention. And in the lower attention, we observe that this was an automatic filtering from the training data detection of optical images covered by some atmospheric effects or clouds, which definitely are contradictory to the SAR. And actually, if we let in the algorithm remove this attention layer, which is separating contradictory from positive simultaneously examples, definitely we have a much better recognition of the data. Now, I go to the next approach, the generative models. So generative models are used in computer vision, and we can generate today almost anything. I mean, we can reproduce pictures with very, very high visual accuracy. Even you are not able to separate in between generated image and the original picture. It's the same for text, for other signals. We can copy, I mean, the model is learning from the training data, the behavior, and we generate replicas which are very, very realistic. This is not enough for remote sensing. Why? Because we can generate images which are looking very much similar. So this is a database on ocean patterns by Ifremer in Brest, where we have a different pattern of the ocean. Again, ocean is very challenging, a very typical example of remote sensing, because it's dynamic, it's not observable directly, we don't have training data set. And we have the interest to have generator models, but generators which are equivalent to a simulator in such a way that we can simulate data which is preserving physical parameters. And on this data set was trained a network, a GAN and a diffusion. And we train the network and we make a test for classification. We mixed real images with synthetic images. We apply the classifier for the label data set. And we verify that in terms of classification, the synthetic images, they preserve the same patterns. And that was demonstrated. But ocean patterns, they are influenced by the wind. And we have physical models, which is using the Fourier spectrum of the SAR image of the ocean. So from the spectrum of the Fourier spectrum of the ocean image, we obtain information about the direction and magnitude of the wind and waves. And actually, this generative model we developed, it's a generative model which is preserving this pattern of the spectrum, again, the Fourier transform. They are very simple things, but this Fourier transform contains information, again, wind, direction, and amplitude. And we demonstrated this both for the GAN and for the diffusion model and evaluated. And that is a new direction on generative models, which they are adapted for the physical process. So we have a generative model which generates a multispectral image, but from this image I should be able to extract correct spectral indices, for instance. So these are another example of wave patterns. And that is a toy example. So generally we are doing prediction looking to the future. But in here we have been training a network with an historical map from 19th century. We used an aerial image of the city, and we generated back in time the image, the satellite image of the city in the 19th century. So this is an interesting application in everything which has to do with heritage, historical reconstruction in climate. So we have today many sources of information, historical sources, which could be translated in satellite image. Might be not important visually, but it's important because in this prediction, backward prediction, we can estimate parameters which are not anymore observable. So in climate research, that could be a very powerful tool to use existing information of any type and make prediction of parameters which today we are measuring from a satellite. So that is again this idea of virtual sensing. No, because in this implementation of digital twins, we are using sensors of different resolution. And even Sentinel-2, it's an example of sensor which has bands of 10, 20, and 60 meter resolution. And Sentinel-2 somehow is responsible for amplifying the research in super resolution. So until Sentinel-2, super resolution was a field which was very clustered, let's say. After Sentinel-2, it's in space. There are many teams which are working on super resolution. That becomes, has a practical approach now. So actually, what is spatial resolution? So the spatial resolution of a sensor, it is a property of the sensor. So it's not the property of the image. Many of the publications in super resolution, they refer to image quality. But again, image quality is a visual property. And we discussed about physics aware. And again, resolution is a property of the sensor. It's a bandwidth of the sensor. So in the upper left, we have the sensor model, which is a bandpass filter. And as the input of the sensor, we apply a delta function. Delta function is a model of a small detail, because super resolution means to separate small details, spatial details in the images. And definitely as the smallest details, a delta function. And we have the output of the sensor, which is a sink. And if we have a low bandwidth, the output of the sink has a large main lobe and spreading side lobes. If the bandwidth of the imaging system is large, in this case the output has a narrow sink. And that is observable in the synthetic aperture radar corner reflector, which is almost the ideal delta function. In reality, it is observed with a low and large bandwidth. So the upper image, it is a low resolution, and the lower it's a much higher resolution. And for optical sensor, it is again the area disk, which is a polar representation, or the separation of the details in the circular radius. In the center, where you have high frequencies, the low bandwidth system, it's smoothing the image. In the high bandwidth system, the high resolution, the system, it is, the center part, it's very well resolved. And now the problem of super resolution, it is how to extend the bandwidth, because the system is a low pass filter. This means I don't have the frequency, I do not observe frequencies outside the physical system. And the question is, how can I extend it? And in the past, the super resolution was always based on a strong hypothesis, like maximum entropy, a number of targets, type of the target. In general, was not a solution. Today, because we have this property of machine learning to learn from huge volume of the data and make prediction. This was a prediction of an unobserved data. Because finally, super resolution, it is to predict something which was not observed. So the question is, what I generate to put where I do not have observation. But at this time, this question is done in frequency domain, not in the space domain. So super resolution, it is a prediction. These are examples of super resolution. And I show these examples because super resolution has many, many ways to be understood. So if we have a single pixel camera, like a terahertz imaging, in there I have a problem of super resolution because I have a point detector, I have a scanning system, which is focalizing to this point detector, and later I have a computational imaging, like a compressive sensing, which is reconstructing the image. And in here I need the model of the system, because the model is not model computed. It's the same synthetic aperture radar. We have the example on the bottom left, where we have a bistatic radar, and in the bistatic radar we have information in the side lobes. Generally that is not used, but if we take the information in the side lobes and we complete, and this is real information, it's not artificial generated, in this case we obtain super resolution. This target, the red one, it is much better localized. Tomography, synthetic aperture radar tomography, it is a super resolution because I have assumption that the scene is not changing, mainly buildings, and I have multiple observations with diversity in the look angle in the phase, and I'm super resolving the target. So I obtain precision of millimeter in reconstruction of 3D reconstruction of buildings. But many other methods of super resolution for spatial resolution, they depend on this strong hypothesis. So like Gibbs random fields, total variation, maximum entropy, many methods have been developed. However, this super resolution is not responding to the question how I fill the bandwidth. And now with deep learning, we transform the problem of super resolution in a problem of prediction. So it's not anymore reconstructing the spectrum with some strong hypothesis, it's learning from the data. Of course, super resolution should be always accompanied with a measure of trust, because even I have a huge training data set, a huge diversity in the scenes, not all the instances of the data are predicted with the same accuracy. So these are examples of, again, very simple networks, which was applied on Sentinel data. It was applied actually to predict a missing band. So the experiment, the study started like this. We took Sentinel data, we train the network, later we extract a band, and we generate the missing band. And actually, when you generate the missing band, we generated actually the full resolution, because a missing band could be a 60 meters, but a 60 meter was reconstructed at 10 meter resolution. And this study, actually, it's a study which aims at the transfer in between different sensors. Because I have multispectral data or hyperspectral data, which they do not have the same spectral bands. And with this method, we can generate a spectral band which was not observed. We have a training data set, and later we generate the spectral bands. And when we generate the spectral bands, we automatically generate the full resolution. So it's a prediction, missing or disrupted, corrupted bands, and as interpolations, generations, the missing pixels. These are examples in the upper part of radiometric correction. Sentinel-2 has, if you see this band on the left upper part of a difference in radiometry. So this band was reconstructed, corrected radiometrically. The lower band is 60 meters to 10 meters. And both of them, they are correcting radiometrically, so an artifact correction, and super resolving the band. Yes, for sure. So if you want, we can take a break now. Okay, we take a break until, because I don't know if the coffee break is already open. If the coffee break, quarter of an hour, is okay? Okay, we come back in quarter of an hour. Thank you for. So I continue with only a few slides on super resolution, and later we'll continue with how all these algorithms, they are now implemented, deployed in a digital twin. And the part of demonstration. So that is another super resolution. And one of the questions in super resolution, it is related to this definition. So super resolution, resolution of an imaging system is defined by the bandwidth of the system. And in here, we included the point spread function of the system in the algorithm in such a way that you can verify this VALD protocol. When we generate, we have a loop. And in the loop, we pass through the model of the system, and we compare the error according to the transfer function, to the point spread function, modulation transfer function. And that's it's a condition to respect the physical properties of the super resolved data. These are examples of super resolved data, and these super resolved data, they preserve the consistency of the spectral indices, because that is again the physics aware. So we can super resolve an image to have better spatial detail, but we want to ensure that if we compute spectral indices like vegetation or water indices, they are further consistent. So when we make the prediction, the predicted pixel, they should be correctly reproduced radiometrically. Yeah, that is the architecture with the VALD protocol implementation. I go now for synthetic aperture radar only very fast. If there are questions, please ask the questions. So in synthetic aperture radar, we trained a network with TerraSAR-X at 3-meter resolution and apply the model to Sentinel at 20 meters. And we generated a super resolved image with a resolution approximated by 6 meters. It's an example of the generated SAR image. So this study was a study on detected data. So I would close in here as a part of physics-aware algorithms. And if you have questions, and I will continue with a presentation on how these methods, these algorithms, they are now used in a digital twin, and how the digital twin is operated, and definitely if you want to play the game to help to operate on the digital twin by yourself. Yes?
Have you tried to embed like actual physical equations into
No, not in my team, but we are following. Sorry, not in my team, but we are following this. We are working with colleagues in France, and could happen that's not really demonstrated successfully. So we are working on this, but that is a very important aspect. Okay, another short movie. This time with no sound and no explanation. I'll let it speaking. Good. It is from the same movie as the first 2 minutes. It's about climate change, satellite observation, and collecting and later interpreting the data. Now I go to present a concept of a digital twin for climate change adaptation. This concept has 2 components. So first is responding to the challenges of the climate change, as everyone knows today. And it's integrating part of analyzing, prediction, simulation, and visualization. And it's responding to the challenges of the climate change adaptation at the effect of climate change at the scale of human activity. Because climate change has a global scale, spatial, all the Earth, and it's going over many hundreds of years. However, there is a niche and with a very huge impact, which are the effects of climate change at the scale of human activity, 10 meters to 100 meters and few days to 1 month. Why? Because in here, the climate models, they cannot be applied. So the diversity of this phenomena is so huge that we need very specific models. And these are the models with many parameters, which are models learned from the data. And we now try to make the interface in between the climate change models and these local models with a huge diversity. And that is a role of artificial intelligence. So we go from the scale of 1,000 kilometers and tens of years to the scale of tens, hundreds of meters and days to months. I make a short description of the project. So the project is a project to establish a competence center for climate change adaptation. The competence center will be a unit of the university. And to make it effective, we build it a federated system of digital twin. So here the first particularity, it is adaptation as a scale of human activity. And the second, we are not willing to design a large digital twin. We have a federated digital twin system, in which it is spatialized, and the digital twins are communicating, because there is information which is relevant for water quality, but the same information can be also used for predicting of the risk of mosquitoes. And we have spatialized models communicating and changing information between the different modules, components. This is a general diagram on how we collected the use cases, because we started the design of the federated system in a dialogue with the users. And the users are coming from very different, there are colleagues which are working in life sciences, in biology, medicine, veterinary medicine, because they are affected and they know the models of this pathogen which are spread by mosquitoes and ticks. And they understand the habitat and the factors which are influencing the habitat of insects and also pathogens. We are working with colleagues in Earth physics because they have very different sensors. And it will be an example. We are complementing satellite imagery with seismic measurements. Why? Because seismic measurements are taken continuously. Satellite is observing every few days an area, and we want to transfer and extract information from infrasound, for instance, which to be a warning for the next acquisition of the satellite. We designed the architecture based on the user requirements. The architecture has a layer of data collection, a layer which integrates the artificial intelligence and physical parameter estimation, and a platform interactive for the operation by unexperienced users. We started with an area on the Black Sea and Danube Delta, because this area has a huge diversity, from urban water bodies, hilly forest, and definitely the Danube Delta and the Black Sea. So we have a huge diversity of features. We built it a time series beginning with 2017 until 2023, and we continue to extend it. These are examples of parameters which are extracted and the spectral bands from this data. All these data, they are analyzed in a time series. So we built time series of images and the corresponding parameters which was estimated from the data. We estimate parameters for the water surface, like cyanobacteria, chlorophyll, turbidity, water indices, water color. For the Black Sea, we estimate the currents. So these are examples of the parameter for inland lakes, and they are observed on time series, and they are correlated and analyzed together with time series of climate meteorological data, temperature and precipitation, in such a way to detect causalities and relation in between the phenomena. For the Black Sea, we estimate the Doppler, which is the sea surface currents, and the wind and waves from the synthetic aperture radar. From sensors on infrasound, which are on the board of the Black Sea, we detect anomalies, and we detect storms and strong weather effect. These are time series of temperature and precipitation, which are correlated with the rest of the observations. We observe time series. It's a lake which was during a drought period lost all the volume of water, and we are doing classification of drought using a climate parameter and correlate with satellite image time series in the digital twin. We are using this virtual sensing. So there is a jetty operating LiDAR operated on the International Space Station, which is measuring the canopy height, but the sensor, it is experimental. We don't have a full coverage, neither spatial, neither temporal. So acquisition are sporadic in space and in time. And we trained a network with LiDAR and applied it to Sentinel. And now from Sentinel, we have a canopy estimation. And it's a sensor, it's a virtual sensor, because Sentinel is not measuring in 3D. On the left, we have the Sentinel image. On the right, we have the canopy. Blue to yellow, it's the height of the canopy. And we calibrated the algorithm. And we have now a full operational, like a virtual LiDAR operating from Sentinel-2. For the case of One Health mosquitoes, we are interested in the speed of the wind, and the best wind speeds are provided at 10-meter altitude over the terrain and also over the ocean. We are interested on the continent for mosquitoes, and we are doing a prediction for the height of the wind at 2 meters, because this is the habitat of mosquitoes, and they are sensitive to the wind blow. We operate time series on a synthetic aperture radar, measuring the currents and the wind speed from the data. These are example of time series and the variations, the backscatter in several points, showing the temporal evolution over the lakes and Danube Delta. This is an animation on the top of the wind speed obtained from the meteorological data, and on the bottom is a map, time series of wind maps obtained from Sentinel-1 data in real time. For the situation of One Health, we are coupling the models of the insect, the pathogen, and how that is transferred to the people, and we are working with medical institutions for monitoring and having these models. That is, let's say, the didactical model for an habitat of mosquitoes that I suggested for an exercise to imagine a similar scenario. And to compose this model, we are extracting the time series of the canopy, and we are also, because the insects, they have preferences for certain areas of vegetation, we are looking for the time series of temperature, because our colleagues working on life science, they told that pathogen and mosquito population it's multiplying very fast. If 3 days consecutively, temperature is in between 26 and 30 degrees, and we have this threshold and combine with the other parameters. That is another map of the vegetation index in time series combined with a canopy, so which is a state of the vegetation. Only canopy is not enough to characterize the habitat. That is a 3D representation of the canopy for the area. That is again the time series of the canopy. I'm sorry that I copied 2 times. This I would, if you allow me, I will let it for discussion. I will skip it now. It is a part of active learning. So if someone is interested, at the end I will present it with some movies. That is infrasound measurements. We have infrasound sensors which are assembled at 20 Hertz, and we analyze streams of 48 hours during the strong storms affecting the Black Sea coastline. From these signals, we extract spectral parameters, again, Fourier analysis, characterizing the components of the infrasound. And these are examples of the parameter and the evolution over the time. And we have very long data streams. And based on these parameters, we make query by example. We identify a certain portion, and we ask where and when it happened, the same event. Why? Because these signals are, again, like synthetic aperture radars, they are far to be visual. So analyzing this signal, we need tools. And that is a tool which we select a certain time interval, and we detect when similar events have been produced. So these have been, let's say, the components which are now integrated in the digital twin. And if you allow me, and if you have also your computers, I will enter the system. If you want to accompany, so that is the website. So DTA climate, UPB.ro. Yes, I don't know how to do it. Could you get it? Thanks. Now, I explain the structure. Okay, the system is under construction. Again, any suggestion you can formalize and later send to me via email. I will give you my email immediately. It's extremely useful. And mainly if you can build this kind of didactical example, a scenario on the system. So in here we have the data sets. So if you enter on the data sets, we have biophysical parameter for vegetation. Sentinel-2 for Dobroja, it is this region, the name of the region. Sentinel-1 for the Black Sea. We have land cover maps. environmental parameter is not yet included, in situ data, biochemical parameter for water, and Sentinel-2 and sea currents. Mamaia, it is a resort, the name of a resort on the Black Sea, and a test. Now I'll start with, I'll go over each of them. So in here you have the footprint of the time series of Sentinel-2. So on the upper you have the time moments, the samples in time. So from 2070 to 2023. Acquisition are not periodic because it depends on the cloud coverage. In here you can animate, so you can go on the time series forth and back and observe the changes, the evolution, the parameters which are changing. In the data layers, you can have the true color. So in here you can visualize only the true color image. It's just the visual for visualization. And also you can select a polygon layer to be overlapped, in which you can select polygons with forest or polygons with lakes. And here you have the polygon which is overlapped over the data. And of course you have the zoom in, zoom out buttons. The next data set I go to the parameter. So that is a canopy height map. Again, the canopy height is estimated from the Sentinel-2 data in the time series, and you can observe the evolution of the canopy height over the time. For the canopy height, you can, for all the other parameters actually, you can pin a point. Sorry, that was. So if the value is null, that means it is no data. And actually, for this point, in this corner, you see the evolution of the canopy height over the time for the measurements. If I'm choosing another point here, you have to choose a point which is not null. And I have the value, and the time series will be overlapped with the previous one. One could compare time series evolution. You can also, it takes one moment, you have a transparency button. You can make to visualize a map and the physical parameter extracted in the data. Now appeared the time series in the second point, and this can now be repeated for all the other data sets. I go to the next data set. Yes. So these are the Sentinel-1 data. Sorry, I'm operating with only one hand. I enter again. Now that is a time series of Sentinel-1 covering the part of the Danube Delta lakes and the sea. These are ships which are anchored here. And again, you can navigate in time, have the time series, observing the change of patterns over the Black Sea surface and the Danube Delta. So that's actually, this visualization refers to the intensity of the VV polarization of Sentinel. And you can change to the wind field. And for each of the acquisition of Sentinel-1, the system will display the wind field. If you observe what I'm observing now, a delay, please, in the notes you are generating, make this observation. So this is a wind field. And again, this wind field now can be observed over the time series. And we have the sea current. So the wind field, it is obtained from the Fourier spectrum of the intensity of the Sentinel. The sea current, it is extracted from the Doppler of the complex value of the Sentinel. And in here you see the map of the sea current. It's loading the data. And again, you can observe the time series, the same as in the previous. You can pin and verify evolution of the data. And I go to the data set again. And I will stop with biochemical parameter of water. And in here you have the watercolor, the dissolved material, the chlorophyll, cyanobacteria, and so on. So you have the list of 7 biochemical parameters which have been observed. And again, for each of them, you can extract the variation in a certain point. And you have the time series, the animation. You can follow this in time. So it's loading the time series in here. So this is a time series for this point. And you can compare data sets. So in here, on left and right, you have exactly the same data sets as before, but I can make a comparative study. So I can take, I don't know, I take Sentinel-1 for delta, and I give another example. I take the biochemical parameters for the same area. And now you have the time series Sentinel-1, a regular one, because it's independent of atmospheric. And you have the time series of Landsat. And you can extract now and compare at the same time moment or evolution of the patterns in between these two. And I let now your imagination. And definitely any criticism, suggestion are very, yes.
Some questions. I joined on the second half because I didn't know that this workshop is very interesting. But I was wondering, so as I understood, you're using JEDI data together with Sentinel-1 and Sentinel-2 to basically train a model which would predict canopy height from Sentinel-1 and Sentinel-2 data. do you somehow validate the results of the model and
Yes.
what are the results?
Yes. Okay. The model is trained from Jetty on Sentinel-2, not on Sentinel-1. Maybe in the future will be Sentinel-2 also, Sentinel-1. But for the moment, it's Jetty Sentinel-2. From Sentinel-2, we extract height of the canopy, and we validated this with airplane LiDAR data, very high resolution. Because we are one of the parameters we extract it is carbon stock, and for the carbon stock we need to make correction because I give a practical. If there is a road in the forest at 30 meters, we obtain from Jetty and Sentinel. We do not have a precise, and we are going. That is not yet here, but we are going to make a correction in terms of porosity of. And we validated the model with airborne LiDAR data. I can show you an example of validation data. And also we validated with forestry information. We have we have a map of species, a polygon map of species. And for each of the species, we have the age of the species. And we have evolution of oak or pine, and we validate it also by species.
Okay, no, like, do you have some numbers, like how accurate the height is? Because generally, if you, like for the local, let's say, area, it is fairly, easy with some method, but when you sort of scale it up, then it's very sort of uncertain.
Yes. Wait a second, I have to search in my archives.
But I have some more questions.
Yes, good. I collect the questions. One question, it is calibration.
Then I saw you're using intensity data of Sentinel-1, which I understood you're using this complex data for some of the applications. Like there's the real and imaginary part of the intensity, so we're using SLC.
Yes. So, yes, go ahead with the question.
Yeah, and then when you do the processing, why do you specifically visualize intensity over, let's say, backscatter sigma 0? Because intensity doesn't account, let's say, for the thermal noise or instrument noise. So is there some like specific reason why it is intensity and not backscatter?
There is no reason, we just did it like this. But that is for visualization. So because visualization is still adaptive to our visual perception and will not be, this data is calibrated to be visual. So this data is converted to 8 bits because a 16-bit intensity I cannot display. Dynamics too high. And finally, if I'm backscatter or intensity, after doing adaptation for visualization, that is lost. But in processing, we are using, for what is now on the screen, for the wind speed, we are using the detected data correctly, and we have a processor for wind speed with corrections and noise, because in there, the wind speed is obtained from the Fourier spectrum of the data. And for the sea current, we work with singular complex data because we need the Doppler. And we make Doppler estimation. We have two algorithms on Doppler, Madsen, and Doppler correlation. We validated both of them. And,
Okay. Have you encountered any, let's say, issues with the geocoding accuracy of Sentinel-1 data? If you do the calculations in the radar coordinate system, or if you do the, let's say, terrain correction, then terrain correction might, let's say, impose some additional, let's say, geometric faults.
in this case, we are. Here we are lucky because it's the sea. In the land, we are going to use the Sentinel also for the mountain area, not yet here. And in there, we need to have all the gamma correction and everything. And,
Okay, thank you.
if there are other questions, I go to search the slide with the calibration. could you write me this? I keep in mind, but please, when you are doing this scenario.
I'll write it, sure, but
Yes.
is that possible?
Yes, that is coming. The system is coming. The system is under work, and we have something in mind. I mean, this is clear. They should be synchronized. Yeah, but I'm collecting also. I mean, that happens that we have been put it on the list, but I'm sure this would be things we never have been thinking. Please excuse me, as long as I'm searching in my archive, I disconnect. So this is the airborne LiDAR data we used for validation, for comparison with centimeter precision. And this is one plot of the 30-meter, which was extracted from Sentinel. And we did all the calibration measures. I cannot find, we have the error interval even for species and for different areas. I can try to find it. So if you have other questions, and in parallel, I can try to find the other examples. The article is going to appear sometime in JSTAR, IEEE transaction on a journal on selected topics on remote sensing. This is a plot of predicted versus jetty measurements. So in the point where you have the jetty measurements, we compare. Yeah, okay, arrived. Was far away. We validated against the predicted data from Sentinel with the jetty original data in the points where jetty measurements exist. not on the training point, with, as always, and in addition to the airborne LiDAR. And this is a plot Jetty against predicting. Yes.
Is it the pixel-based model in your case? So you basically predict the highest resolution pixel which you have contained. Did you consider any kind of, let's say, compartment based on the forest shape model? Because why I'm asking is because that data is quite noisy. So when you do the pixel-based prediction, it might happen so that actually, well, some of the data is getting, let's say, affected by the noise more than the rest, which ultimately basically makes the model worse. But if you're using, let's say, some sort of spatial averaging, let's say for the forest compartment, which is presumably more homogeneous, then it might remove the effects of the noise.
Yeah, I mean, from this work, we learned many things. And that's actually, I'm not sure if it's exactly what you are thinking, but I'll be glad if we can cooperate at some time. So what we have now for the next step, we want to make these corrections and this training using pre-classification of species. Because we observed that we have different errors depending on the type of crown. And that is because LiDAR is scattering differently on conifers and is scattering, we studied over the time from winter to, over the season. And we have definitely clear differences of scattering. And this, we are now going to make a training specialized per type of species. So first a classification and training per species, and might be also for temporal. But again, this is a new project. And definitely I keep in mind your suggestion.
I'm just asking.
Any question, it's information. I'm not looking to your screens. I let you to be completely independent. So I repeat also, what I ask, if you can look into the system, if you can imagine a scenario. So what could be, you're the first time looking, also the area probably is not known to you, but based on information you have in the system, if you could make a micro project to be something meaningful, composing these maps of information and the time series, if you could imagine a small scenario, and please send it to me via email. I'm giving you my email now. We have colleagues which are willing to download the feature, the maps, because they have other tools and they want to import and to use it. And this button will appear. So if you have any further question, don't hesitate.
Similar data coverage for the time range, because we see that a lot of it's hard to do comparison, because for the same, for example, if we would like to same point in time compare what is in, for example, Sentinel-1 wind and biochemical parameters of water, but they are in different time periods calculated.
No, for the moment, the time series for optical Sentinel-2. It is from 2070 to 2023, and there are some interval of higher density, mainly to the good weather, clear sky. The Sentinel-1, it's on a shorter period. Okay, it's periodic because it's radar, but for the moment it's.
The environmental parameters are not ready yet, or I mean, for example, here I'm looking at the soil moisture. So either the results here come from a very low resolution image, or
The soil moisture is loaded from Copernicus land services. And you are right, for the moment visualization is not very well, the contrast is not enough, but the values are correct. But please, if you make a note, that will be very much helpful to have it, not for myself, but yes, just write an email. No, these are the jetted points. Yeah, they are not really in situ, but yeah.
but the other layers here, which I can select, some results of models.
Yeah, they are from the models. Yes. No. They are predictions.
So I have one more question for this height, basically counter-height prediction. Do you also have some sort of publication or not?
There is a public. I mean, we are going to publish the results now. It's JSTAR. It's coming probably in 1 month. We don't have a publication. There is a previous work which was done by a group at ETH Zurich. If you search in internet ETH Zurich canopy jetty, and you'll find the publication. It is a team of Konrad Schindler. Sentinel-2 canopy jetty. And the first author, it is Konrad Schindler, yes. And we started with the algorithm, and we enhanced the estimator, putting all this condition of calibration.
this and also the time interval. I mean, what's the reason for that?
Yes. So I answer that to everyone. So there is a forest for which we use a canopy height to estimate the carbon stock. And that was done because we had a different model for estimation of the carbon stock, and it was prototype only on this parcel. And I tell which is intended application. So we have, I mean, there is a European cartography of vegetation, and we have one for Romania, and we have also polygon with a different type of species, in which periodically, every 5 years, there is new information. For instance, average height or change of the species, and so on, so on. And now we want a carbon stock, and we want now to have this automatized. So in such a way that we can update anytime, compute and update all the polygons.
Okay. Currently, it's being really measured, or is it still something remote sensing based?
No, today that is manually done. There are people going in the field, and they update the cartography. And we want now, I mean, this polygon was on a prototype to show that we can extract the height and carbon stock. And also we want to have the biomass, the parameters, and later for the polygon to insert automatically in the polygon.
So biomass and carbon stock are basically the same, or the curse?
No, they are. I mean, they. No, they are not exactly the same. They depend on the canopy height, but they depend also on type of species. And we have, I mean, after we have the species, we have the canopy height measured now, and we have different models which later they are applied and to estimate these values.
Sorry, it's just out of curiosity. This carbon stock. So which? I mean, they look really the same apart from here from the time series. It looks the same apart from the value. Yes. I don't know if this is something of the visualization or what. But I mean, I suppose that one is derived from the other, right? I mean, is it carbon?
Yes, carbon stock, it's derived from the biomass.
From the biomass.
Yes.
And carbon stock has additionally what?
Could have to study the question. They are linear models. Let me have a look.